less than 5 in permutations and combinations. Here's where my English really gets tested, and it's with the concepts of at least or at most or not in the idea of combination problems. So we're using the NCR formula, but we've got to be careful where the definitions are described or the limits are described. So for example, in class example number 1, I have 11 student council members, 5 are males and 6 are females, and I want to make subcommittees with different recipes. Well, if I have exactly 3 females, how is that going to work? Or at least 3 females. What does at least mean? At least 3 females means I can have 3 females, 4 females, or 5 females. At least 1 female. Well, what does at least 1 female mean? At least 1 female means 1, 2, 3, 4, or 5 females. Exactly 3 females, that's very specific. I must have only 3 females and the rest are males. Choosing the subcommittee doesn't matter in terms of order, but the composition. So exactly 3 females would be 6 choose 3, that's out of the female collection. 5 choose 2 comes out of the male collection. That's 20 times 10 for 200 subcommittees. The at least 3 female collection is a little bit more involved. We've got the from before. Sorry, I didn't record that. C can be solved like B, but it's nice to see another alternative. Take all of your possible committees, which is 11 possible members, select 5 of them, and subtract off the 1 committee that is all males. What you would be left with is all the other committees that have at least 1 female. That's 1 female, 2 females, 3 females, 4 females, or 5 females. Now we get to play with cards. Hopefully your knowledge of cards is adequate. At least 1 red card. We're going to solve like we just solved C. I'm going to deal out 5 cards from a deck of 52. So that means it's 52, choose 5. And then I want to subtract cards that are black. So 52, choose 5. That's all the possibility of red card. That's all the possible hands. And then subtract hands off that contain all black cards. 26, choose 5. We'll do those numbers in a minute. Now I'm looking at the next one for at most 2 kings. Well, I'm going to solve it in the same way that I did B, and that's in the OR situation. Let's set that up. So just talking through the at most 2 kings. The first situation is 0 kings. Out of 4 possible kings, I choose 0. That means out of the other 48 cards, I must choose 5. Or I get 1 king, 4 choose 1, plus 48, select 4 cards. Or 4 choose 2 kings, and then I get my 3 cards from the other set of 48. Just evaluate these numbers. I have my multiplication set up. Now I have to do the subtraction. 52 choose 5 was 25, 9, 8, 9, 6, 0. And I have to subtract the selection of cards that would all be black. That's a result of 2, 5, 3, 3, 1, 8, 0. At most 2 kings is a selection of OR, so that's why I had to add. So 1 times 1712304 plus 4 times 194,580 plus 6 times 17296. So those are plus signs in between. 1 times 1712304, 4 times 194,580, 6 times 17,296 is another crazy big number. It's hard to know whether these numbers are correct. Like it's just envisioning the number of possibilities. unless you play a lot of cards, is probably difficult. Exactly two pairs sets up in a bit of an interesting way. I'll set it up and then talk about it. Okay, talking through exactly two pairs. Well, exactly two pairs means I need to select two cards of the same value. So this is my first pair out of a set of 4 2s, for example. I need to select two of them. Out of a set of 4 7s, for example, I have to select two of them. But I had 13 possibilities for that. So I could have selected anywhere from ace to king, which is 13 possibilities for my pair cards. So that's why I have 13 choose two, which is which number did I choose for pairs, which number is paired. And then I'm left with 44 cards from which I have to choose one. So working those numbers out separately and then multiplying them. So my individual numbers are 78 times 6 times 6 times 44, which is 1, 2, 3, 5, 5, 2. This is a fairly popular question for combinations. Order doesn't matter in selecting toys. I'm just going to play with them. It doesn't matter what order I select them in. Just going to put them in my cabinet. Order doesn't matter. From 10 toys, Fran selects 2, but Bernie selects 8. And it turns out that Fran and Bernie have the same number of ways of choosing those cars. Now, why is that? In words, when I choose 2 out of 10, I'm actually leaving 8 behind, which is kind of the opposite of the operation. And when we look at the formula for NCR, you've got 10 factorial divided by 10 minus 2 factorial times 2 factorial. That's actually equal to 10 factorial divided by 10 minus 8 factorial times 8 factorial. Just the arrangement is different. 10 minus 2 factorial is 8 factorial. 10 minus 8 factorial is 2 factorial. So these are actually exactly the same. And there is a general rule for that. Remember, this notation is a slightly different way of writing the combination statement. NCR can be written as a fraction and R. But N choose R is the same as N C N minus R. And we'll have some opportunity to play around with that. Combinations again. During a Pee-wee hockey tryouts, all the players get to shake hands. Well, there were 300 handshakes in all. How many people do you need to make a handshake? You need 2. And order doesn't matter. How you go around choosing who you shake hands with doesn't matter. But eventually you shake hands with 300 people. If order doesn't matter, can we figure out how many people were there? So N choose 2 means I have to write out my combination notation. So that's n factorial divided by n minus 2 factorial times 2 factorial. We started with this kind of work, n minus 1, n minus 2, keep going down by 1. And then I recognize that I can stop at n minus 2 factorial because n minus 2 factorial will cancel. And 2 factorial is 2, which is nice. So this number is actually equal to 2. So now I can go n times n minus 1 and move that 2 over to the other side is 600. And now I can either FOIL it out or try to determine two numbers that multiply together to get 600 and only differ by 1. You might try finding the square root of 600. That's a really good way of getting close to those numbers. I took the square root, and now I think that 25 times 24 Not quite, that was 24 times 24. 25 times 24 is 600. So 25 times 24 is equal to 600, which means at my Pee Wee hockey tournament, N was equal to 25. So geometrical shapes, putting triangles in circles, putting lines in circles, or figuring out diagonals in pentagons. I could draw and count the lines, no problem. I found that there were 10 lines which I could count. Seeing the triangles is a little bit weird, but it turns out that 5 choose 3 or 5 choose 2 is exactly the same number based on that shortcut from the previous question. Remember, selecting 3 or selecting 2 out of a group of 5 are actually related operations. The polygon question is going to lead us to a new formula which we need to grab today. How many lines can be drawn connecting 2 points on the pentagon, including the sides? So counting the sides up that I drew, I ended up with 10 lines in there. How many of those lines are diagonals? Well, it turns out that the diagonals are only 5 of them. There are only 5 diagonals. Otherwise, they're just edges. So in terms of combinations, we can write this as 10 choose 2 minus 5, or n choose r minus the number of sides. I think I see one extra line in my polygon that was illegal. I'll fix that in a minute. Okay, there's a better looking polygon. There should be a star in the middle. I put a diagonal down there. How many diagonals are there in a regular octagon? Well, we're going to try this formula out. An octagon has how many sides? Sorry, that previous one should be 5 choose 2, connecting my 10. 5 choose 2, there are 5 sides. The diagonal in my octagon would be 8, and I have to choose 2 and then subtract the 8 number of sides off. In a regular n-sided polygon, it would be n choose 2 minus the number of sides. So my previous formula can be improved because my r should be a 2. So here's that shortcut rule. So now we get to try out that formula. N choose 2 minus n equals 65. I'll let you work on it for a little bit and then reveal the answer. So here's how I chose to solve this one using my factorial notation, getting rid of the n minus 2 factorial. Then I thought making common denominator would be convenient because I can't get rid of the 2 as easily as I have in the past. Then I set up for factoring, 2 numbers that multiply for negative 130 but add for negative 3. I know those 2 numbers, and then I throw out the negative 10 because negative n values are not valid here. So that's our last lesson before Christmas. Try it out. It's a short lesson to work on. I do have some practice questions that we can try in addition to it.